Alright, so question number 9. This is the part B about the balancing chemical equations. I may just bunch this all up as a one video since this part is going to be that long. It's essentially the same idea as all the things we've done so far with network questions. There's a one minor difference though, and I will talk about that. But essentially the theory and the idea is the same, right? So in some flows we have this equation, right? And you hopefully took Chem 20 and 30, so I don't have to explain this whole thing in the from the scratch. But essentially, we have this equation, and we're supposed to balance them, right? So, for example, you have this C3H8, O2, CO2, and H2O. In front, I just took my wrote down the coefficients X, Y, Z, T. The reason why I put coefficients now because technically it's just number according to what we know, right? In chemistry, we call those numbers coefficients, but nonetheless, you know. So we want to X, Y, Z, T. That's where we're gonna put the number. We want to put the number so that there is so that all the elements on the left side is the same as the elements on the right side. Elements are, by the way, like things like C, H, and O. Those are capital letters, right? Those are the elements. That's what we call. So C is carbon. You probably heard of those. H is hydrogen. Oxygen is water. No. What am I saying? O is oxygen. Yeah. No water. Water is H2O, which is a different story. But nonetheless, right there. So, yeah. Okay, yeah, good. Oh, technically, because... Oh, no, I was just thinking something else. But anyways, so essentially, yeah. So, for example, here, if there's 3 carbons on the reactant or the beginning side, then the carbon should be also 3 on the right side. For example, I'm not saying there's 3 carbons, but as an example, right? So how do we know, right? How do we know, what are we dealing with? For some of you, it's obvious, but for some people, they may not know what balancing equation is. So I'm just covering all the bases here. So we'll start making the table, and then we'll explain how these equations work, right? So let's deal with carbon. How many carbons are on the left side? Well, here is C3 here, right? That means whatever the X is, right? That's times 3 carbon, right? So let's say X was 1, for example, right? That means 1 times C3, but inside that C3H8, right? There's 3 carbons, so that's multiplied by 3. So that's why I put 3X here, right? 3 carbons here. Are there any carbons here? No, so we skip it. We don't even need one, right? Let's look at the product side, which is the output, right? How many carbons are there? There's 1 times Z. So therefore, there's Z right there. Is there a carbon on height in water or H2O? No, so we don't talk about that. So 3X and Z. That's how we do it. I'm going to go over the O's and H's too, just in case. Oxygen, do we see oxygen in C3H8? Not at all. So we skip. There's O2. Yeah, there is oxygen. So what is this? This Y, but remember how many oxygen are here? Times 2, right? O2. So every time there's Y, if Y is 1, there's 2 oxygen, right? 2 oxygen. So because of that, it's going to be 2Y. Let's look at the right-hand side, or the product, or output, or whatever, right? Here's CO2. Let's look at it. Oxygen, there's 2. So similar idea is this, so it's going to be 2Z, right? Here, there's 1 oxygen, so that's going to be T, right? T times oxygen, so 1-1 ratio, right? And moving on. So H is also the same here, just 8 there, so that's going to be 8 times X. No H, skip. No H, skip. There's H2 here, so that's going to be 2T, right? So that's all there is. After you establish that, it's exactly the same as we've been doing so far with the network. So, put it into linear equations. Here, so you put a linear equation, just put all the unknowns on the left side, numbers on the right. Interesting though, in balancing equation, it seems like it's homogeneous, because they must be balanced, right? In reactant and the product should be the same. So the flow rate, so remember last time we were trying to make sure the flow rate is greater than 0. In this case, the flow rate has to be 0, right? No greater or no less, right? So that's an interesting difference, right? But there's also another difference, so don't go away, right? So because of that, so we organize it nicely, and then we put it into a matrix, reduce the matrix. In this case, it's only 3 by 4. And it's homogeneous too, right? So we should be able to reduce it relatively easily. So I'll just let you follow through this. So ultimately, important thing is, this was as simple as I can reduce, right? So once you reduce this, and then, just put it back to the linear equation, so here, look at it, xz, xy, xt, right? So again, it's just my habit. I like to, here's an interesting thing. So remember in network tactics, right? We would choose the one that's, by itself, right? In this case, it's actually the opposite because everything is connected to x, right? So I want to use x to express everything, right? Does that sort of make sense? Because x something equals to z, x something equals to y, x something equals to t, right? So all the currency is in x. So, if everyone's using that currency, I might as well make the parameter as x. What's a good example? A good example is, let's say, you have to deal with the Russians, the Chinese, and who are the ones who are playing really big nowadays? Russia, China. Is anyone playing really ambitious right now? Enough to matter? Maybe Turkey? I don't know. Oh, Germany, yeah, they're playing a little ambitious with their Eurozones. Nobody talks about it because they're not supposed to be the bad guys yet. That might change depending on how Russians and Germans get along with each other. I'm not sure why it went completely geopolitical. Okay, anyways, that's another passion of mine that I may or may not talk about. But not for this one, because those are not very popular topic right now. But nonetheless, so we keep going. So we have this. So for that reason, back to the analogy. I brought it up, so I have to use it. So, so when you deal with the Germans, Russians, and the Chinese, right? They, ultimately, they all want American dollars. And I know some people might frown upon that, but let's face it, this is a dollar system, so get used to it. I know there are some other countries that are trying to replace American currency, but it's the best we've got. So I'm aware of their printing policy, but again, kind of hard to complain if they're they're the boss, right? Yeah, okay. We'll have a debate about this later. Hopefully nobody puts some controversial comments on this stuff on the comment. But nonetheless, so because of that reason, we want to stick with American dollars so that we can deal with all three players at the same time without causing a lot of hassles or converting or whatever, right? And anyways, so because of that, I actually set x as my parameter, right? So right here, let x become p, So if I do that, then I can define y, which is 5p. You know how to do this, right? So, nothing new. So this is where the difference another difference is felt, right? So you guys can see a little bit better that way. Yeah, sure. So so what did we do with the network? So network, we wanted to make sure these are above 0, right? Well, in this case, we're not gonna be doing that. We want this to be, this is fine. Like, we don't want it to make it greater or less. The only thing we want though is that we don't want this to be 0, right? Because if this is 0, then everything's 0. So that's like saying, I started off with 0 and I got 0 as an output. Yeah, that's great. It works logically, but I mean, where's the use in that, right? What's the whole point of doing COH, right? Company of heroes. Okay, anyway, sorry. Having my nerd moment. Okay, so because of that, so we don't want to use 0, but we want to use something else. And another thing I should mention, here in the balancing equation, the smallest coefficient we can use is 1, right? And it has to be a whole number, right? So I actually sort of wrote out here, the parameter or this or these things should be positive, because you can't have a negative element, right? And maybe we could, depending on how far you went with quantum mechanics, but that's another story too. Okay, I really need to focus. So parameter has to be positive number, it has to be whole number, so no, okay, if you use computer science terms, there is no float or double. This is gonna be integer, right? So anyways, so that's a whole number, and then it's gotta be greater than 0. But at the same time though, I don't want, just because I said greater than 0 doesn't mean it could be any number greater than 0. No. Because if that's the case, then I want these ratio to be as simple as possible. So for example, I don't want 15:5 ratio. I want 3:1 ratio, right? So I want the smallest reduced ratio possible. So it has to be greater than 0, because having 0-0 ratio is stupid. But at the same time, I don't want that number to get huge. So those are the three conditions that we need to think about, right? So my argument is, well, what's the smallest can P be without violating those three conditions? 1. Does that work? Let's see. If P is 1, 5P is 5, right? And if 3P is just 3, and 4P is 4. And as a matter of fact, that actually becomes an answer. So it actually becomes 1, 5, 3, and 4. Now, we were able to conclude that really quickly, just simply because we know about chemistry, right? This is what our professor has done, which is still right, but, you know, maybe a little longer than I would expect. So this is what professor done. So she's got the highest one, right? Just like we did with the network, and divided by 5, right? So then you have P divided by 5, P, 3 over 5P, 4 over 5P, right? So again, because of the rule we talked about, this must be, all of these must be whole number greater than 0, right? So let's look at the smallest one, 1 over 5, right? This has to be greater than 0. So what's the smallest number you can use? What's the smallest P value can you use to make sure this becomes a whole number? That's going to be 5. 5 over 5 is P. Anything less than 5 is a decimal, so we can't use that, right? And 5 is the smallest one that makes 1. So if we go over 5, yeah, we could maybe use 10 or something. But again, that defeats the whole point of ratios, right? So because of that, she argued this way, right? So she said P has to be 5, okay? So, but again, we're using this now, right? Not this. We're using this now, right? So because of that, the first one, x, right? P divided by 5. So we said 5, P must be 5 for this case, right? 5 divided by 5 is 1. P is going to be 5. 3 over 5 times 5 is 3, right? 5 cancels out, so it's going to be 3. 4 over 5 times 5 is 4. So you still get the same answer, but I don't know. Maybe I'm being egoistic here. My method seems smarter because it takes one less step. But again, the gap isn't huge, right? So just go with whatever method works for you, right? So I'll let you decide it. So, but that's essentially the only small difference. So what were the differences? The flow rate is 0 because input and output must be the same. Law of the law of the conservation of mass and energy. So that. Second thing is, instead of trying to make P to E, second thing is the condition for P, right? So what I mean by that, remember the conditions we just talked about? P must be positive number, and must be greater than 0. And in the end, it must be a whole number, right? So those are the three things you need to think about, right? So those are the only two differences. Everything else is the same idea, and as I have shown you. So that's question 9. This is question 10, right? So just follow through. Nothing has changed, okay? So same idea, right? This looks a little intimidating, but again, same thing. There's only one thing that might throw you off, so I'll just go over that just in case, right? So carbon, same thing. 6 carbons here. There's only one player to deal with, so we're just going to use that. 6, 6. And hydrogen is 12, right? So that's 12, right? Here, right side gets a little bit tricky, so let's see. Carbon, there's 2 carbons, right? So 1 carbon times Y plus 2 carbon times Z, right? So that's going to be Y plus 2Z. Does that make sense? Because there's more, yeah, we know that. So that's the easy part. Again, oxygen is going to be 2 here and 1 here, so there's 2Y plus Z. Now, the part where it gets a little bit tricky for some of you who are not used to chemistry is the H here. So here H is out here, but wait a minute, what is this? C2H5OH. So there's H5 and then there's H. What is going on? So don't get confused. It just means 6H for our purposes. The reason why we separated, we could talk about that. Then that's where we diverge into organic chemistry. Very primitive organic chemistry, not the ones that are taught in college level. But nonetheless, I could talk about it. But again, that's not the whole point. We're trying to solve the problem, right? So let's stick with that. If you want to learn more about it, I don't know if I'll be making chemistry videos, but surf around. It's pretty easy to find. Just Google or whatever. So anyway, for our purpose, so H5 and H is going to be just same thing as 6H. So we're going to just put 6Z, right? Z times 6H, right? And then after that, everything's straightforward. Now, I don't know if we're allowed to do this. Basically I was supposed to make it as a linear equation and just convert it to matrix, right? Well, I saw some pattern and I thought maybe I could still solve this algebraically without indulging matrix stuff, right? So this is so this is just relatively simple algebra. So this is what I did. So I said 6x. So what I noticed is, wait a minute, these two inputs are the same. So technically, if this equals to this, this equals to that, then technically isn't this equal to this, right? So that's where I let off, and I actually summarized it so that, so when I did that, I realized z equals to y. So then all I have left is z equals to y and 2x equals to z. So after that, then I can just say, if I say x is a parameter, then it's going to be x equals p, z is 2x, right? So it's a 2p equals to z, and that z is equal to y, so 2p. So I actually just figured it out right away, right? So here, I divided by 2 because that's our professor did, but you get to decide. I think it should be 1, 2, 2, but same idea. Oh yeah, no, we can't do that. Oh yeah, no, it's 1, 2, 2. So yeah, if I divide that, so that it becomes like this, then p has to be minimum 2, right? So 2 divided by 2 is 1, 2, 2. 1, 2, 2. Right? So if you do that, it balances out, right? If you did that, I don't know, if I was a prof, I would give you marks for that because it works, right? But again, I'm not the prof, so. This is how your professor would probably do it because this is still a linear algebra class, right? So basically, as soon as you have this, instead of just working through algebraically like me, I'll just convert it into the matrix, and you should be able to see that, oh, wait a minute, these two look similar, so these should cancel out, just like you cancel out for me, right? So just go through these, and this is my most reduced form. Now I could put this into a proper, echelon format, but again, that's not the point here, right? So you could, I might ask a prof too, but again, putting it into reduced form is not, putting it into reduced echelon form is not the goal here, right? So I just got here, so again, I put, so there's nothing to do with here. So I'm just converting this back to linear algebra questions. Oh wait, this happens to be the same as what we were dealing with here. So we have the same answer. X equals to z, 2x equals to z. And then, I didn't write it here, but it will go back to exactly the same thing as that, right? So I'll just write it just in case. So it's x. So let x be p is real number. You guys can see, right? Yeah. So then there's going to be, so then y is going, what am I doing? So this will be, so 2p equals to z, and z equals to y, so y also equals to 2p. And that's exactly the same thing as what we saw here. So, nothing more to say. It's, it's solved, right? Okay, so last one, which is 11. No, 12, sorry, yeah. 11 is the same idea, it's just I'm getting a little tired and I have to go soon, so. But it's the same idea. The only difference is you have fluorine. So instead of doing COH like we used to do on the table, you're going to have F. So it will make your matrix a little bit bigger perhaps, right? But again, it's the same idea though, right? So we're going to look at 12, just follow through. Nothing new has changed. Nothing new is introduced here, right? Same idea. I want to make sure you guys can see everything clearly. Yeah, there we go. Okay, but that's all there is to it. So that wraps up 1.9. Again, there's other fascinating stuff. I really, if you're trying to minor in electrical engineering, I don't know, just in case when you go to U of C, or if you're just interested, because we have to deal with circuits a lot when we actually learn about the computer hardware, that would be kind of cool. But again, I think you get the idea so that you don't actually have to do the applications, because we see the big picture, right? What it is about. But yeah, but anyways, yeah, I might do it, like I said, I'm being repetitive, I know, but I might make more videos about that because some of the applications we really missed out. Oh, man. But anywho, that covers 1.9, so hopefully this helped you a lot. I understand for people this year, I posted this a little late. This week has been hell, but yeah. Anyways, but hopefully this will act as a note for the final, and for the other classes who have not taken a quiz 2 yet, this will be helpful. So hopefully. Anyways, yeah, so there is. I will see you in 2.9.